All right, guys, and welcome back to class. All right, so we're starting a new unit. I'll call it Unit 7, but it doesn't matter. And the topic, what we're really after this time, is we're going to be looking at electricity. And so if you look at electricity, look at the very root of the word electricity. It's rooted in this word electron. The word electron in Greek, the only difference is it's got a K in it instead of a C. But this word electron in the Greek actually means amber. And so this is a piece of amber that we're looking at down here in this picture. If you've ever seen Jurassic Park, the guy had a piece of amber with like a little mosquito trapped inside of it. But what the Greeks noticed is you could take, say, a piece of animal fur. You could take a piece of animal fur and rub this amber with it, and what would happen is they would notice its ability to attract or repel certain objects. Now, what they didn't understand completely, obviously at the time, is that electrons were being transferred to this piece of amber. And by transferring those electrons, this piece of amber was becoming negatively charged, while the fur was becoming positively charged. And so we've experienced the same thing. If you've ever taken a balloon and rubbed it against your head and noticed its ability to stick to the ceiling or to the wall, and if you've never done that, go get a balloon right now. I order you and blow it up and rub it against your head and start playing with it. It's tons of fun, especially during a pandemic like this. Anyway, as we're moving through, notice what I've got next. I know you're like, hey, Mr. Cole, this isn't chemistry class, but here you are talking about protons, neutrons, and electrons. Well, if you're going to understand what electricity is, you obviously have to understand this little foundation of what the atom is made out of. Now, we know that the nucleus itself inside the atom is made of the protons and the neutrons. And the protons have the positive charge, whereas the neutrons have the neutral charge. And then out here in this cloud around her, in these sublevels, that's where the electrons are. And what happens, these electrons, it's pretty easy in certain atoms to literally separate those electrons from the atom. That's exactly what happens when we do chemical bonding and things like that. It's also the foundation of electricity, the ability to actually move these electrons from either one atom to another or from one object to another. And so you keep hearing me use this word charge. So there's a definition for what charge is. Now, charge is measured in what's known as Coulomb. So if you look down here, I gave you a couple of numbers down here. And those are the charges of an electron and a proton. Now, something that's really rather interesting is this. If we're looking at, say, a proton, and yes, we know it has a positive charge, and you're looking at an electron is actually much, much smaller. I'm not drawing this to scale, but the electron has a negative charge to it. Now, what's interesting, the proton, it's got a mass, and if you're working problems, you'll have to have this mass. The proton has a mass of 1.67 times 10 to the negative 27 kilograms, whereas the electron, much smaller, 1/1800th that size. The electron has a mass of 9.11 times 10 to the negative 31 kilograms. So you notice a very difference in their mass. But now look back up here. This is the charge of a proton electron. And what you're going to notice is this. Look at the charge of the proton. The charge of a proton is positive 1.6 times 10 to the negative 19 coulombs. And then the charge, and I wrote the letter M for whatever reason, but the charge, Q, the charge of an electron is equal to negative 1.6. So the magnitude, you've got the exact same magnitude of charge. The only thing that's different is the positive and the negative that we see in front of us here. Now, let's look at Coulomb's law. Most of us have a little general understanding of Coulomb's law because we've all heard the whole opposites attract thing. Well, this whole opposites attract and likes repel, yeah, that's got to do with Coulomb's law, but that's about charges. That's really got nothing to do with human beings and their interactions. But oh well, we'll let people say what they will. So look at the formula, and I've given you the formula for Coulomb's law up here. But as you look at that formula, if you've studied physics, you should notice it looks very familiar to a formula you've seen before. So you've probably seen, if you're at this chapter, you've probably seen a universal gravitational force equation, big G, M, little m, over r squared. You may have even seen like m1 and m2 instead of this. But usually we use that equation for when you've got two objects, like let's say maybe the Earth and maybe the Moon. And you can use that formula, the gravitational constant, 6.67 times 10 to the negative 11. But you can use that equation if you know the mass of the Earth, 5.98 times 10 to the 24, and you know the mass of the Moon and this distance between, you can calculate that force of attraction between these two objects. Well, when you look at Coulombs force, and we usually call this like the electrostatic force, it's basically the same thing. It's still a field force. Now, I'm going to do one thing and make this a little bit more politically correct this time. In theory, when you write this formula, your Q1 and Q2 are in absolute values. That's because the positives and the negatives, they don't have anything to do with the mathematical answers that we get in solving these problems. So a typical problem would be something like you have a 3, let's go micro Coulomb particle here, and a 2 micro Coulomb particle here. And you're probably looking at this like, Mr. Cole, why'd you throw in the micro Coulombs? A Coulomb itself is an actual big number. Most problems you work are either going to be in micro coulombs or nano coulombs. Just remember that micro is 10 to the negative 6 and nano is 10 to the negative 9 if you're called upon to do any problems using that kind of stuff. But essentially, the only purpose of the positives and negatives, let's go and let's do this. Let's assign these a charge. So let's say that the 3 is a positive 3 micro Coulomb charge, and the 2 is a negative. In terms of solving the problem, if we wanted to plug into this equation and actually find the force, plugging it in, that's got nothing to do with the positive and the negative. All that tells us is that opposites attract, so it tells us direction. So as you solve these problems, we'll call this force between 3 and 2. As you solve these problems, all you're going to do is use the charges to tell you the direction that these forces are going. A very common thing would be then to give you like another particle out here, say a negative 6 micro Coulomb particle over here. And so then what you might be asked to do is try and figure out, well, that's positive and that's negative, so it means these two attract each other. So you've got this force between the 3 and the 6 this way. And again, I've got entire videos devoted to doing this. But all you do is find your two forces and you get your directions, which tells you to subtract the differences between those two forces. So where do we get this concept of static electricity from? Well, static electricity, it's this ability to basically acquire electrons. There's a little fet from the University of Colorado. I love it. It's called John Travolta or John Travoltage. And if you notice, as you rub John Travolta's foot against the carpet, you see this excess in charge building up on John Travolta. Now let's move his arm a little closer. Ouch. And you'll notice what happens is this. As you build up the extra charge on John Travolta, you've got an excess of negative here. The door, on the other hand, has a lack of charge, so these charges won't balance out. And this is this concept of static electricity. And if I reach a certain point, that's when the discharge will happen. Of course, if you can build up enough charge, getting crazy. I'm a boogeyman, boogeyman. Sorry, having a little 1970s flashback for a moment. But anyway, you've got this idea. There was once a Family Guy skit where it actually...
Dad! I am not your dad. I am Electric Man.
So we noticed the same thing in Peter's skit. As Peter was rubbing his feet across the carpet, he was acquiring this extra charge. And so what actually is going on here, as this extra charge is being acquired, what happens is this extra charge is going to be transferred to the other person. And so some people have this concept here? Well, the deal is that charge is not created or destroyed. It's the same thing. All you can do is transfer the charge. So in this case, we would transfer the charge from one object to another. And so a couple of things like where you'll see this used, lightning is a good use of it when we refer to this separation of charge. And somebody has always asked before, like, well, where does the buildup of charge come from? There has to be a rubbing. If you've ever gotten out of your car and touch the outside of your car, and let's see if I can get a nice little car here. Wow, I should be an auto designer. But what's happening is the car, if you've ever been shocked by your car, what's actually happening is this. The car is rubbing something. The car is rubbing the air. The car is rubbing the air as it goes down the road. And so that excess of charge, remember, you've got rubber wheels, that excess of charge is being built up on the outside of the car. So when you get out and touch the car, that's why you feel the shock upon leaving the vehicle. Now, in terms of lightning, you got to remember, where is lightning formed? It's formed in clouds up in the sky. And so you got the same thing. Just like your car can pick up charge, the cloud itself picks up charge. And sometimes what will happen is there'll become areas inside the cloud even where you have an imbalance of charge. And this is when you'll see like lightning up in the sky. But sometimes you'll also see that lightning as it comes down from the sky as well. And one of the things they know now is that like a bolt of lightning is actually made up of two discharges at the same time, one going up and one going down. So it's kind of interesting how all that works. Now, kind of moving along, I think, and we'll close the video, is because one of the best examples we have of static electricity is this Van de Graaff generator. And the electricity, and I would suggest if you're really interested in it, you go find some videos and you can watch explaining how this Van de Graaff generator works. What's interesting is actually Roll Tide. It comes from a guy from the University of Alabama, or he worked there at one point. This goes all the way back to like the 1930s. And a lot of people wonder, like, so this guy just invented this thing to like shock people is all it is and make people's hair stand up? He actually used this because it creates, some of these can create anywhere from 200 kilovolts of potential. And I know we haven't talked about that yet. Just know that's a lot. All the way up to 500 kilovolts of potential. So there's a lot of voltage can be created by this object. Now, what's interesting is this. He did not make it to make people's hair stand up. Although if you're wondering why the hair stands up, you can imagine that you've got this buildup of charge in the hair and the charge is repelling itself. So what's actually happening with the Van de Graaff generator, the way it's working, it's actually friction down at the bottom occurring between a roller and a belt, and it's creating this positively charged belt that's going up to the top, and it's even picking up more positive charges from the ionized air. If you've got one of these, just know the belts don't last long if you use them because you're actually creating plasma. You're creating like a charged air down at the bottom. And so that charge, that ionized air, actually kind of eats away at the belt. So they don't last long. A lot of teachers buy these things and they think the belt will be good for like ever. No, you'll usually get like maybe one or two, like one semester use out of that belt, and then they go down pretty quick after that. But anyway, it builds up this excess of charge on the surface, and then that's where we kind of see our electricity. You'll have to excuse my coughing for whatever reason. Van de Graaff, on the other hand, like I said, he didn't build it for this purpose. He actually built this to use for like a particle accelerator so that you could develop high-speed velocities with particles and take a particle and then slam that into another particle at high speed using these potentials. So anyway, we'll pick up with some more about electricity after this, but this is kind of like our foundational unit. So anyway, thanks for watching. We'll see you later. Bye.